time is a useful illusion your mind manufactures. The now in real time doesn't exist in the literal way you assume. In this video, we'll show why your present is a biological fiction you can't fully escape. Think about it. We live chained to the clock, watching seconds slip away like water through our fingers. Yet the awkward truth is that your brain is editing reality as it goes. Over the course of a day, you lose roughly 40 minutes of nows, gaps your mind quietly patches over so experience feels continuous. Stretch that across a long life, and it adds up to thousands of hours of stitched together time. Not missing memories, but manufactured ones. Henry Van Dyke caught the feeling. Time is very slow for those who wait, too swift for those who fear, too long for those who grieve, too short for those who rejoice. But for those who love, time is eternity. So what does it mean? Time races or drags because you don't just measure it, you create it. And once you notice it, everything shifts. Brace yourself. The journey is dense but necessary. There's a legend whispered among the most advanced civilizations in the universe, the tale of the star whale. They speak of a formidable creature that can open an abyssal mouth and swallow entire solar systems in a single gulp. They say a casual sweep of its tail could topple empires in seconds. The oldest libraries of the cosmos keep ancient books filled with sketches of this great leviathan, drawn from rumors and half-heard reports. Its hide is said to be tough as leather, studded with barnacles made from stellar material. Even its vast baleen plates are described as speckled with interplanetary plankton, accumulated over what to us would feel like billions of years. To us, because the star whale travels as close to the speed of light as a massive object can. And when you move that fast, time itself behaves differently. Our ordinary sense of now begins to look like a local trick of biology, not a universal fact. For the star whale, the long history of the cosmos compresses into a fleeting instant. The whole human story fits into less than a blink. Every war, every invention, every lost love, every child's laugh, gone before its higher senses would even bother to register it. Follow this creature, and you start to see the real point. The now isn't merely mysterious, it's wildly subjective. And you don't need to be an intergalactic whale to feel it. Picture a car speeding down a road towards a flock of pigeons that seem absurdly calm. From your point of view, the birds are about to become a smear on the tarmac. Then, at the last possible moment, they scatter cleanly into the air. Why did they wait so long? They didn't. Not in their experience. A pigeon's present is not your present. Many birds process visual information far faster than we do. They live in something closer to slow motion, taking in more frames of reality each second. Where a film might feel smooth to us at a few dozen frames per second, a bird can register changes at well over 100. That extra resolution helps them track fast insects, dodge predators, and, yes, move out of the way of a moving car. What looks like a last-second escape to you can feel like generous time to them. Your own now shifts too. In fear it narrows. In play it expands. Under adrenaline, the brain samples more detail, stretching a moment into slices. In boredom, it smears. What feels like time is the rate at which experience is updated, not the ticking of clocks for living minds. So the now can stretch or shrink, depending on what you are doing, and how fast you are moving. Which leaves the uncomfortable question, what is the now really? Does it exist outside your nervous system at all? Or is it something your brain manufactures to make reality feel continuous and survivable? Have you ever wondered what outer space would taste like? While stars wheel through the void at dizzying speed and the fabric of reality keeps stretching, the universe turns out to be strangely sensory. Imagine we drift into the shadow of Sagittarius A star, the giant black hole at the center of our galaxy. Not far from it, about 390 light years away, astronomers study a dense cloud of gas and dust known as Sagittarius B2. Inside that cloud, they've identified ethyl formate, the same molecule that gives raspberries much of their flavor and rum its distinctive aroma. There's even a perfume designed to imitate the smell of space, a sharp blend people describe as burnt meat, gunpowder, and welded metal. But whether the star whale enjoys any of that is beside the point. It, like us, is trapped inside a nervous system, and this is where the idea of now starts to break. The way your senses interpret the world has consequences you rarely notice. Picture yourself in an elegant restaurant. You take a bite of something exquisite, and your brain floods with pleasure, so you think. The truth is that the pleasure is not instantaneous. When food touches your tongue, signals travel along cranial nerves into the brainstem, pass through the thalamus, and arrive in a small region often called the gustatory cortex. That trip takes time. Studies suggest the brain registers taste roughly 100 milliseconds after contact, so the flavor you experience is already a slice of the past. The same is true for every sense you trust. When you grip a heavy fork, signals travel from your fingertips at around 75 meters per second. That's fast, but it is not magic. By the time you feel the metal in your hand, it has already been there for more than 100 milliseconds. Again, you're experiencing the past. Smell is slower and messier still, because molecules must physically move through air before they ever reach your receptors. You never smell the present. You receive a trail of what something used to smell like a moment ago. Storms make the lag obvious. Light can cover a kilometer in a handful of microseconds, but sound takes roughly 3 seconds to cross that same distance. That is why you can estimate how far away lightning struck by counting the seconds until the thunder arrives. Your eyes and ears are, in a quiet way, time machines, each working with a different delay. Even a mirror does it. Light has to leave your face, bounce off glass, and return to your eyes. The round trip takes only a couple of nanoseconds, but it still means you are not seeing yourself now. You are seeing yourself as you were a breath ago. The delay is tiny, yet the principle is brutal. Your present is always a reconstruction. On human scales, milliseconds feel trivial, but as distances become astronomical, the same effect becomes unsettling. If the mirror were far enough away, millions of kilometers, you could watch a younger version of yourself staring back from deep inside your own past, a gap your mind was never built to intuit. Stretch the distance further, and the present collapses entirely. Everything you know, right down to the light in your room, is a shadow of what has already happened. Even your own thoughts arrive late. The brain stitches sight, sound, touch, and smell into a single scene, then stamps it now. It feels immediate only because the edits are hidden. The present is not a point. It is a buffer you carry everywhere the time. When we look up from our own body to the sky, the gap between what we perceive and what is really happening becomes impossible to ignore. If biology already forces us to live a few milliseconds late, the universe forces us to live years, centuries, and millennia behind. Take the moon, that pale beacon over our nights. It sits roughly 384,000 kilometers away. Moonlight needs a little over 1 second to cross that space, so you have never seen the lunar surface in real time. There is an even more poetic effect called earthshine. On a thin crescent moon, The dark portion glows faintly because sunlight bounced off Earth, traveled to the moon, and then returned to your eyes. For a moment, you are looking at our planet in a celestial mirror, delayed by more than 2 seconds. It is a visual echo of what the world was a cosmic heartbeat ago. Now jump to the sun, and the scale becomes unsettling. Sunlight takes a little over 8 minutes to reach you. If the sun were to erupt this instant, we would have no way to know for those full minutes. We would still feel warmth on our skin and see its glow, living under the protection of a star that technically would already be gone. Our now is always an inheritance. That delay is the great headache of spaceflight. Mars is hundreds of millions of kilometers away, so commands and confirmations arrive late. When Mission Control lands a rover, it faces the famous minutes of terror. By the time a signal says the craft has entered the atmosphere, the rover may already be safely down or already scrap. We receive messages sent from a situation that is already history. Push outward and you meet Voyager 1, the most distant human object, now nearly a light day from home. Beyond that lies the realm of stellar ghosts. The farthest star you can see with the naked eye sits in Cassiopeia and is known as V762. Its light has been traveling for 16,000 years. The photons reaching your pupils tonight left when humans were only beginning to domesticate dogs. If someone there watched us through an impossibly powerful telescope, they would see ancestors who could not write, hunting across plains that are deserts now. They would be watching a dead civilization, a light-built illusion. An Andromeda shows a present that happened millions of years ago, when our ancestors were shaping the first stone tools. The strangest example might be inside your own home. A small fraction of the snow on old analog televisions comes from the universe's beginning. Ancient light left over from the first fireball. So everything above your head is a collection of old photographs, a cemetery of light that may no longer match what is there now. That raises a huge problem. If every corner of the universe has its own clock and its own present, how can we say what happened first? Is there any rule that brings order to this chaos of different times? Einstein's answer is unsettling. There is no universal now. Events that seem simultaneous to you will not be simultaneous to an observer moving differently. Because light has a finite speed, each observer must build now by stitching together signals that arrive at different times. Change the motion, change the stitching, and the slice of reality you call the present tilts. That tilt is not a trick. It is built into space and time themselves. Relativity replaces the old idea of absolute time with a structure. Space-time, where each event has coordinates, and the key invariant is the interval between events. Two observers can disagree about how much time passed and how far apart things were, yet agree on that interval, the causal link. If one event can influence another, they are connected by signals that stay at or below light speed, and all observers will agree on their order. But if two events cannot affect each other, their order is not absolute. Different frames can swap them. That is the secret budget of nature. Causality is the accountant, and light speed is the price of sending information. You can only pay for knowledge with time, because every message needs travel time, even inside your brain. Out there across planets and galaxies, the bill becomes merciless, and the universe forces you to live in delayed echoes. So brace yourself. Once we accept that time is traded like currency, we can ask who sets the exchange rate for us. For centuries, we were convinced that time was absolute, an invisible heartbeat ticking at the same rate for everything, everywhere, for everyone. The idea fit daily intuition, and it was refined in the 17th century by Galileo Galilei. To feel Galileo's logic, the logic that ruled science for roughly 200 years, imagine a sailor standing on the deck of a ship gliding across calm water at constant speed. The sailor places a golf ball on a tee, takes a clean swing, and sends the ball forward, watching it arc away and splash into the sea. From the sailor's perspective, the ball moves at the speed given by the strike. Now picture yourself standing on the shore as the ship passes by. To you, the ball was already moving with the ship before the club ever touched it. So you would say the ball's final speed is the ship's speed plus the speed of the hit. In Galileo's world, both of you are right. Each observer has a frame of reference, and to translate between frames, you simply add or subtract velocities. It is tidy, intuitive, and it works beautifully for everyday motion. Most importantly, time stays the same for both observers. No matter how fast the ship moves, the ball takes the same amount of time to fall to the water for you and for the sailor. Then light arrived to ruin the simplicity. In the 19th century, the Scottish physicist James Clerk Maxwell published the set of equations that changed the story. Maxwell described light as an electromagnetic wave that travels at a fixed speed, a universal constant. Today, that speed is often called c, from the Latin celeritas, meaning swiftness. But Maxwell's constant created a crisis. If light always travels at the same speed, what happens when you launch it from a moving ship? Galileo's logic says it should go faster, adding the ship's speed. Maxwell's equations say it will not. Light refuses to take the extra push. To rescue the old picture, scientists proposed the luminiferous ether, an invisible substance filling space, serving as the medium through which light waves travel, the way sound needs air. If the ether existed, then perhaps light speed was constant, only relative to that hidden medium. Motion through the ether would create an ether wind, and careful measurements should detect it. In the late 19th century, Albert Michelson and Edward Morley set out to test that idea. They used Earth's motion around the sun as their moving ship and built an experiment that turned light into its own obstacle course. A beam was split into two paths, one aligned with Earth's motion and another at a right angle. The beams were reflected back and compared. If the ether wind were real, the beam traveling with Earth's motion should gain an advantage, while the sideways beam should lag, and the difference would show up as a shift when the beams recombined. The prediction was clear. The result was shocking. No matter how the apparatus was oriented, both beams arrived together. Light behaved as if its speed was the same in every direction, regardless of Earth's motion. The ship of the planet gave it no shove at all. That failure was not a small inconvenience. It was the end of the Galilean picture as a universal rule, and the birth of a new one. If the speed of light is invariable and cannot be added to other speeds, then something else has to give. The only candidate left is time itself. Einstein saw the escape route. Nature gives you a fixed budget, the speed of light. You cannot exceed it, but you can spend that budget in different ways. Spend more of it moving through space, and less remains for the passage of time. Keep more of it for time, and you must move more slowly through space. You do not get to keep both at full value. That is the core of relativity. If you race through space fast enough, your clock runs slow compared with someone moving differently. Not because your watch malfunctions, but because time is part of the geometry. The universe does not hand out one global now. It hands out local perspectives, each with its own timing, all constrained by the same constant speed of light. So the strange conclusion follows. Time is not the rigid backdrop Galileo assumed. It is flexible, negotiated by motion, and tied to the limits of information itself. To see how time can stretch like chewing gum, picture a train with perfectly transparent walls, moving at a steady speed. In the middle of one carriage, a person fires a pulse of light straight up from the floor to a mirror on the ceiling and back down into their hand. From their point of view, the light simply goes up and down in a clean vertical line. Nothing strange. It's a neat little clock, one bounce, one tick. But you are outside watching the train rush past. While the light is traveling upward, the carriage is also sliding forward. So to you, the same pulse traces a slanted path. Up and forward, then down and forward. It draws a stretched triangle. Here is where everything turns weird. The diagonal path is longer than the vertical path. Yet the speed of light is fixed and cannot change. So the only way for both observers to be right is for time itself to behave differently. Less time passes for the person inside the moving train than for you standing still. The moving clock must run slow. That slowdown is captured by what physicists call the Lorentz factor, and it's the key to understanding the star whale. The effect does not grow in a calm, linear way. It barely shows at low speeds, then explodes as you approach the limit. Travel at about 10% of light speed, and the difference is tiny. What feels like 100 seconds to you is only a fraction more for the outside world. You could live your whole life and hardly notice, but as you creep closer to the limit, every extra sliver of speed makes a dramatic change. Near 99%, the factor rises to several times. Push to 99.9 and it jumps again. Add one more 9 and it leaps to something that feels almost absurd. The closer you get, the more time stretches. For the star whale, skimming as close to light speed as a massive thing can, the effect becomes extreme. Its now swells. Whole eras for us can fit inside what it experiences as a single vast present. Our history becomes a flicker inside its attention. And there is something even more extreme than the star whale, the photon. For a particle of light, time does not pass in the usual sense. Because it moves at the maximum permitted speed, there is no budget left for time. From the photon's perspective, crossing the universe is not a long journey. It is, in a sense, a single event. The idea of one now giving way to another doesn't apply. Even for us, moving slowly, this elasticity has a strange consequence. Different observers can disagree about what happened first. Imagine a train between two trees, and lightning strikes both trees. Someone on the train may say the strike ahead happened first, because the light from that side reaches them sooner. You on the ground may say the strikes were simultaneous. Both accounts can be consistent, because simultaneity is not absolute. Only one thing remains sacred: causality. Nature makes sure causes come before effects for every observer, unless you could send information faster than light, which, as far as we know, you cannot. But if time is that flexible, and even first and same time can wobble, why does it feel as if we always move towards the future? What is it that gives time a one-way direction? To understand why time has a physical direction, we have to travel to California in the 19th century. In a courtroom, a jury found Edward Muybridge not guilty after he shot the man he believed was having an affair with his wife. He avoided prison, and then, in a twist nobody could have predicted, he helped change the way we see reality. Muybridge went on to pioneer chronophotography. He captured a sequence of still images of a horse in full gallop, showing that what we call motion can be built from frozen instants. Run the frames quickly past your eyes, and time seems to flow like a river. But what you are really seeing is a chain of nows compared against each other. Quiet slices that the brain stitches into movement. The odd thing is that, in Newton's basic laws, there is nothing that demands time must run forward. Film a tennis ball flying through the air and play it backwards, and the scene can still look plausible. Without context, you often can't tell which direction is correct. But other processes give the trick away immediately. A shattered egg does not leap back together. A cold cup of coffee does not suddenly begin to steam on its own. In those cases, time is not reversible. Something keeps score. That score is what Sir Arthur Eddington later called the arrow of time. The arrow points in the direction where disorder tends to increase. The idea comes from thermodynamics, from the insight that you never get all your energy back. In every real cycle, there is waste. Useful energy spreads out as diffuse heat, and the system becomes harder to organize again. This is where entropy enters. Entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged. Imagine tossing several coins that all start heads up. It can happen again, but it is far more likely to get a mix. There are many more messy arrangements than perfectly ordered ones. That imbalance is why disorder tends to grow. And that rising disorder is what lets us line our lives up into before and after. A cracked egg tells you a story. Smoke dispersing tells you a story. Heat leaking from a hot mug into a cooler room tells you a story. The arrow of time is the arrow of increasing entropy. Here's the deeper sting. For us to exist at all after the age of the universe, the early cosmos must have started in an extraordinarily low entropy state, far more ordered than you would expect by chance. That remains one of the most uncomfortable mysteries in physics. Some thinkers offer provocative possibilities. Julian Barber, for example, has suggested a picture in which time could run in opposite directions away from a central Janus point. Whether or not that is right, it highlights something important. The arrow of time is not only a feeling, it is a physical asymmetry that demands explanation. But even if physics gives us a cosmic arrow, there is a place where time becomes more treacherous still. Your own head. Your brain edits, deletes, and invents moments without asking. It smooths gaps, compresses events, and fills in missing frames so experience feels continuous. It can steal minutes from you without you noticing, because the stitchwork is hidden behind the illusion of a seamless now. And that brings us to the final twist. After all the delays imposed by distance and by biology, your own perception may be the most unreliable clock of all. Imagine the star whale at the end of its long journey, stranded on a distant cosmic shoreline. There are no stars left in the universe. Every sun has flared into a supernova and faded away. Atoms have drifted apart. The largest black holes are slowly evaporating, bleeding their last traces of Hawking radiation into an almost perfect vacuum. Nothing remains to mark a day or a year. And yet, even though each of its nows lasted ages, this creature has witnessed more moments than any other being could ever count. When it closes its eyes for the last time and its awareness goes dark, one final question hangs in the silence. Does time keep moving on its own, or does it die with the mind that perceived it? Most of us live chained to clocks, watching seconds slip through our fingers like water we can't hold. But the uncomfortable truth is that your brain is lying to you constantly. Look at a wall clock. The ticks feel normal, until you glance away and snap your eyes back. The first movement of the second hand seems to freeze for a beat. This is the stopped clock illusion. And it happens because your eyes are always jumping. Those tiny jumps are called saccades. While your eyes move, the image on your retina smears. Your brain deletes that blur and fills the gap with the first clear frame it finds after the jump. You don't notice the edit. You only feel a longer now. Each saccade lasts only a fraction of a second, but you make so many across a day that the missing slices add up. You lose real moments, and the brain quietly patches over the loss to keep experience smooth. The trick doesn't stop there. Your brain processes color, motion, and shape at different speeds, so it can't know exactly where a moving object is in the present. Instead, it predicts. It shows you where the object should be, not where it truly was at that instant. That is one reason a fly is so hard to catch. You reach for a position the insect never actually occupied. So how long is the present inside your head? Researchers talk about a subjective present, a window of temporal integration that lasts a couple of seconds. You can feel it with certain ambiguous images. Take a classic drawing of a staircase. At first, it looks like a normal set of steps then, after a short delay, your mind flips it, and the same lines become a different staircase. The switch is not in the picture. It's in the timing of your perception. Something similar happens with film. If the fragments are spaced too far apart, the story breaks. Your brain can only stitch so much into one continuous now before it resets and starts again. The present, as you live it, is a moving buffer, a short span where the brain gathers signals, aligns them, and turns them into a single scene. This process leans heavily on the insular cortex, a region tied to internal sensation and emotion. Hunger, pain, empathy, dread, calm. That is why time flies when you're absorbed and drags when you suffer. Your clock is not a device on the wall. It's the state of your nervous system. And notice the paradox. The universe gives you delayed light and irreversible entropy, yet your brain supplies the final edit. It turns gaps into continuity, and continuity into certainty, so you can act at all. In the end, even if the present is only a fiction manufactured by soft grey matter, it's a necessary fiction. Without it, you wouldn't have a stable world to inhabit, and you wouldn't be here asking whether the now exists at all. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.